Okay. So 15.8, 15.9. Let me do this before I forget. Let me go here. Actually, I don't need to do that. Let me go here. And I'm going to go here. I'm going to add an announcement. Okay, and where's my zoomies? Am I not even in? I'm not. Oh, I'm in. Where the heck is the zooms? Stop the sharing. There we go. Let's get rid of that. Okay, so grab my keyboard here. So exam 3. Okay, exam 3, study guide or 3 study guide? Or should I put chapter 15? Chapter 15 exam study guide? What did I do before? I don't know, I can always go back and change it. Exam 3 study guide. Okay, so students, their third exam will be on October 28th. Okay, October 28th. Third exam will be on October 28th from 3:40 p.m. to 5:45. 5 p.m. The study guide / review posted below. Okay, just want to make sure that we have this, because this is what you're going to need to make sure that you look through for Monday's class. Okay, so I want to insert file. Files. 13, chapter 13, upload the file. Choose file. $280. And review. Chapter 15. Upload. Boom. Nice. Okay, save that. There's a new announcement. Let's look at my announcements. There we go. covering chapter 15. That's how I did it. Covering chapter 15. There. Save. Save. Okay, perfect. So you have the study guide now available to you for chapter 15. Okay. Okay, so let's go over 15.8 and 15.9 today. Okay. Then we have an exam, and then we have one more chapter, the hard chapter. It's actually not hard, it's just the applied chapter. It's just all applied. For those of you that like applied math. Okay, so 15.8. 15.9. Okay, 15.8. Actually, you know what? I don't know. Okay. 15.8. Triple integrals in spherical coordinates. Okay, triple integrals in spherical coordinates. Okay, so what are spherical coordinates? Spherical coordinates. Okay, spherical coordinates, we say that they're a rho, which I'm going to call P again, because I can't seem to draw a rho real well. Okay, P, theta, and phi. Okay, so this is rho, theta, and phi. Okay, and spherical coordinates. So we're going to have a point out in space, but we're going to treat that point as if it was on a sphere. Okay, so this guy's on a sphere. Okay, and so there's a radius r, which is rho. Okay, that's rho. Think of rho as the radius, maybe. If you want to think of it as r, you can. Okay, I'm going to think of it as p because it's just that's the way the book does it, and that's the way that I'm going to say. It's kind of confusing because p is rho is density in the last section, but now it's r. I don't know. Again, it's Stewart. Like I love Stewart. I absolutely love his books, except for this one stupid section. Okay, that's the only thing that I don't like. Okay, okay. So I mean, just use R, right? But there's a reason we don't use R. Okay, there's a reason we don't use R. Why? Because R is the radius of a circle. Okay, is the radius of a great circle, and here's the reason we don't use R. Okay, I'm gonna change this. I don't like the way this looks. I don't like this. Is because why? Because R is reserved. R is not rho. R is reserved for this guy here. okay, which I guess it is rho in this case, I don't know. But they like to reserve r for the radius in the xy plane. So, which on a sphere, they're both the same, but if you were to do this in a cylinder, then r would be, right? So if you're like, oh, what's the, you know, if you have a cylinder that's, you know, so they like to say, well, r is the radius of the cylinder for cylindrical coordinates, and rho is the radius for the sphere in spherical coordinates. So anyway, it gets a little technical, but it's all good. Just think of P as not rho. Let's just think of it as the radius. Let's just think of the radius. Okay, that's it. Just think of P as radius. Okay, and we're not going to use R just because, well, we use R for something else later on. So hopefully it'll make sense. Okay, hopefully it makes sense. It's clear as mud. Okay. So what the heck is phi now? Okay, I understand rho. I understand theta. Theta is this angle here. Okay, on the unit circle, or on a circle. Okay, that's theta. Okay, but what is phi? And phi is the angle. Phi is the angle that's made here. Okay, that's the angle that's made between rho or P and the z-axis. That's phi. Okay, so phi is the angle made by z-axis and P. Okay, it's z-axis and P. Okay, because right. So again, this is r. We're going to call this r. Okay, as the radius of that circle, that great circle, or basically the radius of the equator. And then P is the one that goes out to the various points in space. Okay, now are they the same measurement? Sometimes they are. Okay, but think of this as, well, how would I get this point? Well, this point would be, right? How would I get that point in space? Well, that would be a certain rho, right? A certain radius, and then it would be a degree measure starting at 0, right? And then we'll go all the way out maybe here, okay? And then we have another phi that goes from the z-axis. Does that make sense? Like, let me. It's my diagram's getting a little jumbled. Okay, so let's say that we have the point, I don't know, 1, 1, 1. 1, 1, 1. Okay, we're at the point 1, 1, 1, right? Okay, so this is x, this is y, and this is z, right? 1, 1, 1. Okay, so how would we get that point in space, the point 1, 1, 1? Right, so this would be, think of this like a box, right? Okay, so the box is on there. Okay, so 1, 1, 1. Well, it would go from the center here, the origin out to this, that would be rho, right? That distance would be rho. Okay, that distance would be rho. What's the angle that it would be being made with the horizontal plane? That guy's theta, right? That angle is theta, which would be, in this case, it'd be a 45-degree angle, right? So theta would be pi over 4. Right? So what would rho be? Wouldn't rho be radical 2? I think, right? Does that make sense? Is that what rho is? Okay. You might want to turn your TV off. Okay. So rho, theta, pi over 4, right, with the x-axis, starting with the x-axis. going counterclockwise, right? Okay, pi over 4. And then what would this be in 3 space? I know that that's, right, that is 1, it's up 1. Okay, I'm pretty sure that's radical 2. Maybe not. What's the diagonal of that cube? What's the diagonal of a cube? What's the measure of a diagonal of a cube? Whoosh. Measurement of the diagonal of it. That doesn't even look good. Look good. Is that right? Okay. Yeah, the measurement of the diagonal of a cube. Okay, so this is radical 2. This is 1. Oh, so it's not. It's 1 squared plus radical 2 squared equals, so that's 3. So this is the square root of 3. It's radical 3. So rho is equal to radical 3 in this case. Pretty cool, pretty cool, pretty cool. Okay. So that's nice. Okay, and then I'm not even going to try to figure out what phi is. Oh no, I could probably figure it out because again, it's just, this is 1, this is 1. So what's the angle made here? Well, what is that? What is that angle? Anne? No? Who is doing that to me? Stop it, whoever you are. Okay, just turn your dang music off. Okay, so what would be phi in this case? Okay, well, I have a 90-degree angle. I have radical 3. I have 1, and I have radical 2, right? So I could find out what this angle is. Okay, this one here, right? That wouldn't be too hard. This would be the, I could use any of these. So this is radical 2, and this is radical 3. So what's that angle? Well, that angle is going to be like inverse sine of radical 2 or radical 3. Okay. Wonder what that is. What is that approximately? I don't know, it's just an approximation. I'm basically just screwing around at this point. See what this is. Okay, what is that? Inverse sine. Trigonometry. Trigonometry. Second, inverse sine of radical 2 or 3. Okay, so 2 divided by 3. Radical. And then take the inverse sine of that bad boy. Okay. Okay, and this is in degrees mode. So this is about 54.74 degrees. That's interesting. Okay, if I want it in radians, let's put it in radians. So let's do that again. So 2 divided by 3. Okay, square. Okay, and then take the inverse sine of that, and that's about 0.955, right? 0.955. Okay, so which is going to be, you know, it's not too pretty. Okay, but that is what phi is. Okay, in this example. Okay, so you get the idea. Well, how do we convert? How do we convert from rectangular? Oh, I probably should have done this before I did all this math, but that's okay. Convert from rectangular to spherical. Okay, convert rectangular to spherical. Okay, so we know that x is equal to rho times the sine of phi times the cosine of theta. Y is equal to rho times the sine of phi sine of theta, and z is equal to rho times the cosine of phi. Okay, so these are my conversion formulas. Okay, how do I go from, this is really how I go from rho phi and theta to x, y, and z. Okay, and I also know that rho squared is equal to x squared plus y squared plus z squared. Okay. Rho squared is equal to x squared plus y squared plus z squared. Okay. So number one, okay, convert, I want to convert 2 pi over 4, okay, 2 pi over 4 okay, and pi over 3 to rectangular coordinates. Let's convert this guy. 2 pi over 4 pi over 3. So this is again rho, phi, theta, and phi. Okay, so rho, theta, and phi. Okay, and so we said that x was equal to rho sine phi cosine theta. Okay, y was equal to rho sine phi sine theta, and z is just equal to rho cosine phi. Z equals to rho cosine phi. Okay, so rho here is 2, sine of pi over 3 times the cosine of pi over 4. Okay, y is equal to 2 times, y is equal to 2 times the sine of pi over 3 times the sine of pi over 4. And then z is equal to 2 times the cosine of pi over 4. No, pi over 3, sorry. Pi over 3. Okay, so this is going to be sine of pi over 3, that is radical 3 over 2, right? So this is going to be 2 times radical 3 over 2 times radical 2 over 2. Okay, so this is going to be radical 6 over 2. So rad 6 on 2, as the Brits would say. Okay, and then 2, this is going to be sine of pi over 3, again is radical 3 over 2, sine of pi over, it's the same thing. 2 radical 3 over 2 times radical 2 over 2, and this is going to be radical 6 over 2. Okay, this is x, this is y, and then what's z? Z is going to be cosine of pi over 3, which is 1/2. So this thing just goes to 1. This is 2 times 1/2, which goes to 1. Okay, so these would be the polar coordinates, or actually I'm going to write this as a coordinate. Radical 6 over 2, radical 6 over 2, comma 1. That's how I would represent that in rectangular coordinates. Okay. Okay, let's use these to do what I was doing before, which let's do number 2 here. Let's convert 1, 1, 1 to polar coordinates. Oh, let's see if I can do that. Convert 1, 1, 1 to polar coordinates. Okay, so let's use this. This is, let's find out what rho is first. Rho squared is equal to x squared plus y squared plus z squared. Okay, so how would I find rho? Rho would be equal to 1 squared plus 1 squared plus 1 squared, which is 3. So rho is equal to plus or minus radical 3. I'm going to take the positive of radical 3. There we go. We found out what rho is. Pretty easy. Radical 3. Okay. I used Pythagorean theorem before and, you know, messed it all around, but here, there you go. There you go. It's on a sphere. Okay, let's find the radius. Okay, that's good. Okay, so now what do I know? Now I know that x is equal to rho times the sine of phi times the cosine of theta, and y is equal to rho times the sine of phi sine of theta, and I know that z is equal to rho times cosine of phi, right? Z is equal to rho times cosine of phi. Okay, so how can I solve for phi? Well, right here. I know what z is. Z is 1. I know what rho is. Rho is radical 3. So cosine of phi, okay, so I could easily figure out what phi is. Okay. So 1 over radical 3 is equal to cosine of phi. So if I do the inverse cosine of 1 over radical 3, before I just used inverse sine, right? Didn't I use inverse sine or something like that? I don't know what I did. Yeah, I used inverse sine of radical 2 over radical 3. Okay. So could I use inverse cosine? Yeah, of 1 over radical 3. Yeah, absolutely. Inverse cosine of 1 over radical 3. Look at that. Inverse cosine, okay, of 1 over radical 3, and that'll give us phi. Okay, I'm just going to leave it like that. Okay. Okay, so now what can we figure out? Well, we could solve for well, x is 1, right? X is 1. What's rho? 1. No, sorry, rho is radical 3. The sine of phi, well, that would be the sine of the inverse cosine of 1 over radical 3. Oh, that's interesting. Okay, and then this would be the cosine of theta. Sure, okay. So we want the sine of the inverse cosine. I'd have to draw a triangle for this. Let's draw that triangle we had before. Okay. So I want the angle whose cosine is 1 over radical 3. And then I want to take the sine of that. Well, wouldn't that be radical 2 over radical, what the sine would be radical 2 over radical 3. That's the sine whose cosine is, this is phi, right? So that's phi. Okay, and then the angle whose sine is, because this is just an angle, this is just angle phi. Okay, the angle whose, well, this is just going to be radical 2 over radical 3. Cancel out the radical 3. 1, so this is 1 on rad 2 is equal to the cosine of theta. So theta, okay, cosine of theta equals, oh, look at this, this is radical 2 over 2. And we know that the angle whose, the angle, okay, theta, what did we say what theta was? Was it here? Okay, theta was pi over 4. Look at that. We know that theta was pi over 4. Well, isn't that the inverse cosine of radical 2 over 2 is pi over 4? Yeah, so theta is pi over 4. Boom. Look at that. That's nice. That's how we convert back. Good stuff. Good stuff. How do we integrate with respect to spherical coordinates?
Can you scroll back down just a bit?
Yeah, sure. This was phi. That was theta. And rho, I came out with rho here. Okay. Okay. Sorry. Okay, there we go. Okay, so if I want to do a triple integral in polar coordinates, okay, involving x, y's, and z's, dv, this is going to be equal to, okay, a bunch of stuff, which is going to be fun, okay, bunch of fun stuff. Okay, this is going to be from, okay, c to d, okay, c to d, c to d. This is going to go from alpha beta, okay, and this is going to go from g1 of phi, theta phi, to g2 of theta phi. Can I expand this now? Okay. Okay, of f of, well, what was x? X was rho sine phi cosine theta. What was y? Rho sine phi sine theta. What was z? Well, that was rho cosine phi. Okay, but now I need a conversion factor. I'm not going to go into how we get the conversion factor. Just know that it's, before it was r, right? When we went to polar coordinates, it was r, right? R dr d theta, or even when we went to severe cylindrical coordinates, it was, right? It was r dr d theta. It was d. It was r dz dr d theta, right? We just put in an r. Well, in this case, because we're on a sphere, on the surface of a sphere, okay, our conversion factor is rho squared times sine phi. Okay, this is our conversion factor. And that's going to be d rho, d theta, d phi. Okay, d rho, d theta, d phi. And I keep that in that order, okay, for these problems. Okay, but don't forget your conversion factor here. Okay, it's think of it as r squared sine phi. Okay, but in this case, r is rho. Okay, so. Okay, and again, why do we use rho instead of r? Because say that we get a function in terms of theta and phi, but then I want to, then I get a function just in terms of theta. Well, once I do the rho conversion, I get a function just in terms of theta, or just in terms of, or I do the integration with respect to theta, and then I get a function just in terms of phi, right? Then at that point, I may need to use that function, that angle, okay, to phi, and I might need to find the radius, or turn that into polar coordinates, or parameterize that one, and then we want to put in r. Okay, just because r, we think of r as a two-dimensional radius, rho as a three-dimensional radius. Okay, it just makes it so that sometimes we have to use r as a flat circle radius and rho as a spherical radius, and it makes it easier to think about that, because sometimes we have to think about, well, what's the radius on the flat plane, and then what's the radius on the sphere. Okay. But the fact that they use rho for density and they use rho for the radius of a sphere, that, Stuart, stop the insanity, okay, Mr. Stewart, and your insaneness. Okay. So let's do an example here, number 3. Let's evaluate this triple integral. Okay, B, and we'll talk about what B means in a minute. Okay, B. Okay. 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 Yeah. When we did regular triple integrals, we let B be a box. Okay. If we're going to spherical coordinates, we don't let B be a box. We call B a ball. Okay. This is a ball. Okay. If we're going to use spherical coordinates, it's got to be on a ball. Okay. It's got to be a ball. It's got to be a sphere. Ball. Okay. On this ball, we're going to integrate. We're going to integrate over this ball. Okay. So it's not a box, it's a ball. Okay. Okay. So we're going to go from E of x squared plus y squared plus z squared to the 3 halves dv. Okay, that's what we want. We want it on the ball. And what is this ball? This is we're going to call this the unit ball. That's the unit ball. That's the ball of radius 1. Okay, that's the ball of radius 1. So, okay. Kind of interesting. Okay, so we got to talk about the limits of integration now. Limits of integration. Okay, so let's change this to polar coordinates, or not polar coordinates. Let's change this to spherical coordinates, and then we're going to talk about the limits of integration. This is going to be e to the rho squared to the 3 halves, right? Okay, because isn't x squared plus y squared plus z squared rho squared, right? dv, and that's over that ball. Okay, so the 2's are going to cancel. And so I just get e, okay, e to the rho squared dv. But what's dv going to end up being? dv is going to end up being our conversion factor, dp, d theta, d phi. This is p squared, is it sine phi? I think it's sine phi, yeah. Okay, sine phi, and it's dp, d theta, d phi. Right, dp, d theta, d phi. So this is going to be e to the p to the 3. This is going to be p squared sine phi, d phi, d theta, d phi. I'm sorry, d rho. Sorry, I don't know. I keep saying it's the p's and the ph's and it's messing with my mind today. Okay. Okay. So EP through here. So now, okay. So now what are the limits of integration? Okay. Well, it's on the unit ball, right? It's on the unit sphere. So let's look at the limits of integration on this sphere. Okay. So let's just choose a point on the sphere and let's figure out, I mean, how would I get the entire volume of the sphere? How do I get this entire volume of the sphere? Using, you know, rho and theta and phi. Well, rho is just going to be the radius, right? So rho. I'm just going to go out rho, right? Just go out rho. Okay. Theta is going to be all the way around the equator. Does that make sense? Like take this point that's out rho on the equator and then go all the way around the equator. So let's just go all the way around the equator, right? However, okay, so rho, okay, it goes from 0 to some value. Okay, maybe we'll call this A. So 0 to A, rho goes from 0 to A. Okay, right? because it's the whole thing. It's going to be the whole. I don't want just the sphere. I want the ball, right? I want the entire world. I don't just want the surface. A sphere is the surface. A ball is everything included. Okay, think of a baseball. You're not just hitting the sphere, the surface of that baseball. You're hitting the whole ball. Okay. And so rho goes from, say, 0 to a. Okay, what is theta going from? Theta goes from 0 to 2 pi. But what does phi go from?
0 to pi.
What is it?
0 to pi.
Why? Why is that? Just because you read the book? You gotta
It's
know.
because it's the whole surface of the circle.
Because what?
It's a whole circle. It's a full circle.
Okay, so that explains 0 to 2 pi, but she said that this was 0 to pi. Why not 0 to 2 pi?
Would it be just the top half of the circle or the sphere?
What is, okay, what is, I should really teach this stuff because this is good. It's good stuff, okay? I guess it is good stuff and that's why I teach it. But, okay, so you're gonna be like, oh, this makes sense in a minute, okay? So just, okay, so you can read this in a book, but the book doesn't really tell you like, oh yeah, this is how to visualize it, right? How do you make it, how do you make this make sense to your grandma, right? And you know how I make this make sense to my grandma? Oh, if she was still alive. I would talk about orange slices, okay? Think about the orange slices here, right? Think about the orange slices. How do you get a full orange when you eat orange slices? Right? What does phi represent? Phi represents the angle to a point from the z-axis, right? Does that make sense? The angle from the z-axis to a point. But an orange slice is not a full circle. An orange slice is only half the circle, right? So it's a semicircle. Why? Because you take all those semicircles and then you rotate them around a 360-degree axis. What are you going to end up with getting with all of your orange slices? Aren't you going to end up getting the full sphere? See? See, Wu Yun, did you know about the orange slices, Wu Yun? See?
No.
See, you didn't know. Yeah, you didn't know about the orange slices. Okay. Does that make sense?
Yes.
Yeah, she's like, yes. She's like, thank you. Like, okay. Like, yes, I read it in the book, okay? I didn't understand about the orange slices. It's okay. It's okay. Nobody does. Okay. I'm the only one that understands about the orange slices. Okay. But hopefully this makes sense. What does phi go from? It goes from 0. It could be 0 if your point is at the North Pole. Okay. And then all the way, okay, down here, okay, to pi, right? 0 to pi. Boom. That creates an orange slice, and then you rotate those orange slices all the way around theta, and that gives you your full sphere. Nice.
So is it technically, oh, just kidding, that makes sense. Thank you.
Okay. So, you want me to grab an orange? I mean, it might help. Go grab an orange, okay, and look at the orange slice, and then put the orange back together, and all the way around. Okay. So 0 to pi, 0 to pi, or yeah. Okay. Okay, so, oops. Okay, so what is our, okay, so this is p squared sine phi dp d theta d phi. So what are our limits of integration here? Okay, well, if on the unit ball, what's a? A is 1, right? So isn't this going to go to 1? So that's 0 to 1 for phi. Not phi, I'm sorry, for rho. Wow. Do, re, mi, fa, sol, la, ti, do. Okay. Okay, e, fo, phi, mo, rho, ti, la, I forget it. Okay. So 0 to 1 for rho, okay, or p, okay. Theta is going to go from 0 to 2 pi. I can say theta because that's different than p's and phi's and b's and everything else, okay? Okay, and so with the e's, right, it's like they're all rhyming, right? So I've only dated women whose first names have ended in E, right? And when I got married, I was like, I married and you don't even fit the bill, right? Because the first person was Jenny, and then Sandy, and then what was the third one? The third one was Wendy, okay, and then I married Amanda, like, and I was like, ha! I broke the cycle, okay. I dated Jenny for like a year, Sandy for 2, Wendy for 2. I was even going to be engaged to Sandy, but then she broke my heart. So she broke my heart because she ended up breaking up with me to go out with my best friend in college. So that was, we'll just cross her off. Okay, bitch. I'm just kidding. Okay, I'm not bitter. Not bitter. Okay. She dated the guy for like a month and then called me back up and said, I made a big mistake by breaking up with you. I'm like, yeah, you did. Bye-bye. Yeah. So it was like Jenny, Sandy, Wendy, and then I married Amanda. And then I was like, oh, we don't fit the bill here. You must be the right one. And she says, however, my childhood nickname was Mandy. I'm like, oh crap. Great. It's just wonderful. So like, okay. Anyway, personal trivia. You're like, could you please get back to the sphericals? I'm sure. Sorry. My personal issues with ease. Okay. So it was just a trigger. It was a trigger. It was a trigger. Okay. So, and then this is going to go from 0 to pi. There you go. Okay. So now what are we going to do? We're going to integrate with respect to rho. Okay. And we're going to do a u sub. This is going to be a really nice u sub, because if we do u is equal to p cubed, then du is equal to 3p squared. That's nice. Why? Because I already have, right, dp, p squared dp. I have the p squared here, and I have the dp. Oh, okay. And so this is going to be 3 du over 3 is equal to p squared dp. Oh, okay. So this is going to be, if I change I can change my limits of integration too. It really doesn't matter. Because what's 0 cubed? 0. What's 1 cubed? 1. So this is e to the u, right? P squared dp, that's going to be du, sine of phi d theta d phi. Okay. This is going to go from 0 to 2 pi, and then from 0 to pi. Okay. Okay, so we have EU du sine phi d theta d phi. So, well, what's the integral of e to the u? Well, it's just e to the u, right? Okay. Oh, this was du over 3. I missed that. Thank you. Okay. So this is du over 3. Okay. So this is going to be, the integral is 1/3 EU from 0 to 1. Plug in 1 for u. That's just 1/3 e. Right? Okay, so this is 1/3 e to the first minus 1/3 e to the 0. E to the 0 is not 0, so don't make that mistake. Okay, e to the 0 is 1. So what does this become? This becomes 1/3 times e minus 1. Okay, times the sine of phi d theta d phi. Okay, integrate from 0 to 2 pi and then 0 to pi. Okay. Okay, and then 1/3 e minus 1. Okay. Okay, and so this thing is just a constant. I can pull that thing out. Okay, I can pull that thing all the way out to the front if I really wanted to. Okay, so this is just 1/3. What's the sine phi? Well, that just involves phi. It doesn't involve theta. So this is 1/3 e minus 1, right? Times the integral of 0 to pi. If I integrate on theta, well, this is treated all as a constant. Okay, so integrate on theta, we would get theta times the sine of phi. Okay, evaluated from 0 to 2 pi. Okay, and then that would be d phi. Okay, so this is going to be 2 pi sine phi. Okay, 2 pi sine phi. Okay, nice, nice, nice. And then I'm going to integrate that from 0 to pi. Okay, and I've got this 1/3 e minus 1 on the outside. D phi. Okay, so what's the integral of sine? Well, that's negative cosine, right? So this is going to be, I'm pull the 2 pi out in front. So this is 2 pi over 3. Okay, times e minus 1 to the negative cosine evaluated from 0 to pi. Okay, cosine from 0 to pi. Okay, so what are we going to do here? Okay, let me actually do it like this. So the cosine of, oh, this is phi, sorry. Okay, the cosine of phi, and then we're going to evaluate that phi from 0 to pi. So the cosine of pi, well, that's -1. So this is the negative of a -1 minus the negative of, well, what's the cosine of 0? That's 1. So minus a -1. So this is the -1, which is +1, minus the -1, which is another +1. So this is just going to be 1 plus 1, which is 2. So I'm going to multiply that. I'm going to get 4 pi over 3 e minus 1, which is approximately what? What is this approximately? So this is going to be 4 pi. Oops, clear that. Clear. 4 times pi divided by 3, parentheses. This is screwing up on me. Okay, I'm going to go 4 divided by 3 first. Okay, yes. Times pi, yes, is that, times, parentheses, e, where's my e? E, nope, I got to do it reverse notation. 1 e, oh, you know what, that's not the right e. Let's go back. So this is 1. Let's go second e to the first power, that's good. Okay, minus 1. Close parentheses equals, and that's about 7.19, I'll call it 7.2 for good measure, about 7.2. Okay. Okay, let's do another one of these since we're having so much fun. Okay. Number 4. Okay, use spherical coordinates to find the volume, to find the volume of the solid. Gosh, why is this so big? I need to reduce my pen size. Move that over. Stop. There. This, I'm going to change this to, oh, that's already like that. Okay, good. Let's change that to the other red. Okay, perfect. Okay, use spherical to find the volume of the solid, okay, that lies above the cone. Z equals square root of x squared plus y squared, and below the sphere, x squared plus y squared plus z squared equals z. Okay, interesting. Below the sphere, x squared plus y squared plus z squared equals z. That's interesting. You got 2 z's there. What's up with that? Okay. Z squared equals z. Okay. So what the heck is this thing going to look like? We have this thing, and we have this thing here, this cone, z equals the square root of x squared plus y squared. Okay, so let's see if we can draw this thing. Okay, let's focus on the sphere first. Okay, let's focus on the sphere first. What happens when x and y are 0? Y and 0. So let x equals 0 and y equals 0. Then we get 0 squared plus 0 squared plus z squared equals z. Okay. So when is z squared equal to z? I could pull z squared minus z is equal to 0. I could factor out a z. I get z minus 1 equals 0. And so, oh, okay, I know that z equals 1 or z equals 0. So I have the point 0, 0, 0 or 0, 0, 1. Okay, so what's the sphere? What's a sphere that contains both of those points? What does that look like? Okay, I have a sphere that goes through this point, and I have a sphere that goes through this point. Okay, so wouldn't that be a sphere that looks like this? Right, this is 1. North pole is at 0, 0, 1. South pole is at 0, 0, 0. Oh, okay, that's kind of cool. Nice, 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 nice. Okay, cool, cool. I like what I've done there. Okay, so that's the sphere that we're looking at. Okay. So, right. Where are these? Where's this point? Where's the equator? Any idea where the equator would be? Well, it would have to be halfway for z, right? Wouldn't z equal 1/2? Right? So z would equal 1/2. I know that. Okay, so let's see. Where the heck is that equator? That's going to be x squared plus y squared plus z squared equals z. Okay, so x squared plus y squared plus 1/2 squared is equal to 1/2. That's interesting. Okay, so this is x squared plus y squared is plus 1/4 is equal to 1/2. Okay, minus 1/4. Nice. And I get x squared plus y squared equals 1/4. Ah, that is r equals 1/2. That's the radius of a circle of 1/2. Oh, that's kind of cool. Okay, so this goes out here. Okay, so this is up 1/2, and this is out 1/2. So that point there, I could say is 0, 1/2, 1/2. Oh, that's interesting. That's kind of cool. That makes sense that the radius of the sphere would be 1/2, right? So what is rho? What's rho? We just figured out what rho was. Isn't rho 1/2? Right, goes from 0 to 1/2. Nice, 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 nice. Okay, so what about this? What about the cone? What about the cone here? Okay. What about the cone? What's the cone? The cone is this thing here. Okay. And so let's think about this for a second. When x is 0 and y is 0, okay, let's look at the cone here. When x is 0 and y is 0, then z is 0. Z is 0. So we get the point 0, 0, 0. Okay, so that's the cone. Okay. And then how far out can this cone go? Well, the cone can go out as far as this equator, right? So it kind of looks like this. Okay, now why is it on the equator? It doesn't necessarily have to be at the equator, right? But why would it be on that equator? Okay, why would this be, why would that be the equation here? Okay, well, let's think about it this way. Let's square both sides. Let's go z squared equals x squared plus y squared. Okay, that's reminiscent of the equation of a circle, right? So this is a circle, and if I were to center that, that's a circle centered at 0, 0. That's a circle centered at 0, 0 with radius z, right? With radius z. Ah, okay. So that's so this cone's going to be made of these concentric circles, right? Of radius z. However far as z is up, that's the radius, right? Well, however far up we go, that's the radius. So if I go up halfway, then that's the radius. If I go up, you know, a third of the way, then that's the radius. So the radius and z are equal. So it basically looks like this. Okay, you've got basically an isosceles triangle that are creating your, that's creating your cone, right? That's an isosceles triangle because the height, z, and the width, radius, are the same. Oh, that's kind of cool. Okay. So we want everything that lies above this, but below the sphere. Okay, so what is that? What is that? What does that look like? Well, it looks kind of like an ice cream cone, to be completely honest with you. Right? Isn't that really what we're looking for? It lies above the cone, but below the sphere. So it really is this whole solid. Okay, and we want to find the volume of that. Oh.
If it's the like volume above the cone, why does it include the cone, if that makes sense? Like, wouldn't it just be the scoop part, like the top part, if that makes sense?
Because the cone does not include its volume. A cone is a surface. When you think of a cone, really, this is what you should be thinking of. And the cone is the surface here. Does that make sense?
Sort of. I'm just a little bit confused about the wording since it just says lies above the cone, but it includes the cone.
Yeah. So here,
Okay.
let me help you out here with the wording. Okay, again, how the hell are you gonna explain this to your grandma, right? You're like, Grandma, let me teach you about cones, Grandma. You're like, she's like, okay, dear. Oh, what's a cone? And you're like, let me show you with a piece of paper. And you're like, okay. And then you're like, what's a cone, Grandma? And then you're like, see this, Grandma? See? Okay, bold of you to assume that I'm smarter than my grandma. Yes, it is a bold claim. Okay, here's my cone, right? My cone is this surface, right? And then you're like, Grandma, I made this for you. And you're like, what? What did you say, dear? I can't hear you. I'm old and decrepit. I said, Grandma, I made this cone for you so you could hear me. Stick it in your ear. Right? So this is the cone. See how this cone is the bottom of the surface? It's the bottom of the solid, right? Think of your ice cream cone. It's all the ice cream that goes in here.
Oh, that makes sense.
It's
So it's like
on
open.
that surface.
Oh, so it's just like you were saying, it's just like an open cone. So everything inside is the volume included.
Yes.
Okay, perfect. Thank you.
Does that make sense? Here's my cone. Okay, here's Sunny. Okay, whatever. Anyway. It's good stuff. These are hard concepts. I mean, I know I make fun, but this is not easy stuff. Okay, if this was easy stuff, everybody would be doing it. Okay, everybody would be engineers. Okay, everybody would be mathematicians. Okay, and they're not. Everybody is not engineers, and everybody is not mathematicians. Okay, why? Because this crap is hard. This is some hard stuff. So I don't even make fun or poke fun. I mean, I enjoy your questions, okay? Because I had the same questions, maybe even last week. I don't know everything. I had to figure all this crap out myself as well. So, like, how am I going to? Again, I'm really I don't think of myself as much smarter than the average person, which that's why. Yeah. Anyway. I'm not smarter than the average person. I know some things. Okay, that's it. And you can know those things too. Okay, so we have this entire ice cream cone. Now, how do we find volume? How do we find volume? Well, we can use the triple integral, right? The triple integral here. Okay. Okay. And then what's our function? What's our function going to be? Our function is going to be 1 to find the volume, right? And so then we're going to use our conversion factor rho squared sine phi d theta d rho. So the hardest part of this is going to be figuring out what the heck are my limits of integration. That's going to be the hardest part here. Is the integration is easy. It's finding out, well, what's rho, right? What does rho go from? What does theta go from? Okay, and what does phi go from? Okay.
Is the integration or the triple integration of 1, would that be the volume of the entire sphere? Or like what exactly does that represent here?
This is just represents volume in 3 dimensions.
Oh, right. Okay.
Okay. So if I have a 1 here and I do a triple integral, that means I'm taking a 4-dimensional object and I'm taking a 4-dimensional object and I'm stopping it after 1 second of time and I'm taking a snapshot. It'd be like if you had an expanding ball, right? Say you have this expanding ball and you took a picture at t equals 1, then you'd only have a 3-dimensional object. Okay, right? So, an analogy would be, if you take, if you take a square and you bring it up, okay, or bring it down, then you end up with a volume. But if you take that square and you do a snapshot, you just look down on that square, it's a 2-dimensional area. Okay, so whenever we put a 1 here, we go down 1 dimension. Okay, so basically saying, what's the volume of our domain? Okay, what's the area of our domain? What's the distance of our domain? We're basically saying, what is the measurement of our domain when we put a 1 in here? Okay. It's a way to do that. Okay, so yeah. So how are we going to figure out, okay, rho here? Okay, so we have this cone, okay? So we have the sphere. Let me draw it again. Okay, we have the sphere. And then we have a cone inside the sphere. Okay. Now we want to get, okay, we want to get let's first talk about phi. Okay, let's not even talk about rho yet. Let's just talk about phi first. Okay, what was the definition of phi? Phi is the angle of the point with what? With the
axis.
z-axis, right? It's a z-axis. Thank you. Okay, z-axis. Okay, so what's the angle that's being made here with the z-axis? I'm going to do a different color. And that's a really cool problem. Personally, I think it's a cool problem. So, because like, what's the angle that's being made here? With right? So where are we going? We're going from here to here. That's it. That's it. That's the angle. Right? Because every single point on this, okay, every single point on this thing, think about this slice right here. Okay, if I were to just look at this slice, I'm going to get rid of these dots. I don't need them. Okay, if I were just thinking about this slice right here, what would happen if I took this slice and rotated it 360 degrees? Wouldn't I get the whole ice cream cone? Right, if I rotated about the z-axis, wouldn't I get the whole ice cream cone if I just took that slice? But phi is what angle now, though? What angle is it? Well, how can we get this triangle here? Well, isn't that an isosceles triangle? This is an isosceles triangle. And what's the angle? What are the angle measures of an isosceles triangle? Aren't they 45, 45, 90?
Yes.
Yeah, so what is phi? Phi goes from 0, which would be this point, all the way down to this point. And so phi goes through an angle of pi over 4. Okay, so phi goes from 0 to pi over 4. Oh, okay, that's kind of cool. Okay, so that's going to give me my whole ice cream cone. Okay, what about theta? Theta is the easiest one, right? Isn't theta easy? Totally easy. Okay, theta goes where? 0 to what?
To pi.
2 pi, exactly. Very good. Okay, it's 2 pi, 0 to 2 pi, because we're just going to go all the way around to create that. We're going to go all the way around to create that ice cream cone. Okay, the hardest one here is rho. And we're like, okay, how the heck are we going to get rho? Okay, where is rho going from? Well, rho is going from 0. Rho of 0 would be at the origin, right? That's 0. How would I get any of these points? All these points on this surface. How would I get any of these points on this surface? Let's draw a different line, different auxiliary line. Okay, to one of these points on this surface, right? Okay, so what is creating that surface in terms of rho? How could I represent that surface in terms of rho? Okay. Well, let's look at the equation here. Yeah, rho's kind of a beast. Rho is going to go from 0. Make that a little bigger. Rho is going to go from 0 to something. It's going to be a function. Okay, it's going to be a function of phi. It's going to be, I already did phi. I'm sorry. This is rho. I don't know what I'm doing. Okay, this is rho. Rho is going to be a function of phi. Okay, and how do I know that? Well, aren't all those points on the surface of the sphere? Aren't all those points on the surface of the sphere? And what was the sphere? What was the sphere? The sphere was x squared plus y squared plus z squared equals z, right? Okay, so, okay. Okay, so let's change this all to spherical coordinates. Let's change this to spherical coordinates. Okay, so what is x squared plus y squared plus z squared? What's x squared plus y squared plus z squared?
The equation of a sphere?
No, the equation of a sphere is x squared plus y squared plus z squared equals rho squared.
Oh,
I'm just saying, what is this part? What's that equal to?
rho, oh wait, rho squared?
Rho squared. Yeah, it's equal to rho squared. Why? Why is it equal to rho squared? I don't know. Let's prove it. Let's prove it, Charlie. You know, I don't like to leave things just up open question. I'm like, how the heck did they get that to be rho squared? How do they know that's the equation of the sphere? How did they get these spherical coordinates to begin with? Right? Some mathematician, 300 years ago was like, I'm just going to come up with some sort of brainchild that says, oh, what's x? X is rho times the sine of phi times the cosine of theta. Let's square that bad boy. Plus, what's y? Y is rho times the sine of phi sine of theta. And let's square that bad boy. And then plus z, which is rho cosine of phi. And we're going to square that bad boy, and we're going to see what we get. Okay. Okay. So what's this going? This can be rho squared times sine phi, sine squared phi, times cosine squared theta plus rho squared times sine squared phi times sine squared theta plus rho squared times cosine squared phi. Okay, so what I'm going to do now is I'm going to factor out a rho squared. Let's factor out rho squared. We get sine squared phi times the cosine squared of theta plus the sine squared phi times sine squared theta plus cosine squared phi. Okay, cosine squared phi. Okay, so on these two, I'm going to factor out the sine phi. Sine squared. So sine squared phi, so factor out a rho squared, sine squared phi times cosine squared theta plus sine squared theta plus cosine squared phi. But what is this? What is cosine squared theta plus sine squared theta?
1.
1. Thank you, Wu. Okay. Can I call you Wu? Is that okay?
You can call me Wendy.
I can call you what?
Wendy.
Wendy.
Yeah.
Okay. That's fine. Thank you, Wendy. Okay. I'll remember that because that's one of my ex-girlfriend's names. Okay. I'll try not to think negative thoughts about you with regard to my ex-girlfriend, but this is all good. It's all good. Okay. I'm mature enough to do that and move on. Okay, so this is 1. 1. So Wendy says 1. Okay. I'll just think of you as the delicious hamburger place that has those delicious baked potatoes and those delicious frosties. What is a frosty anyway? I don't know what it is. So that gives me deliciousness to think about. Okay, and then what is this thing? Well, that thing's 1, right? Isn't this 1? Right? Yes.
Yes.
That's 1. And so what does this thing become? It becomes rho squared. Look at that. That is some beautiful mathematics right there. That's amazing. I love it. I love it. I love it. Okay, so this whole thing is equal to rho squared. Okay, so what's z equal to? So this is going to be, okay, so x squared plus y squared plus z squared equals z. Okay, so this is rho squared is equal to rho times the cosine of phi. Oh, okay. Okay, so what is rho? What is rho? Well, I could divide by rho as long as rho is not equal to 0. And I could say rho is equal to cosine phi. So rho of phi is equal to cosine of phi. That's the equation in spherical coordinates. That's the equation of my sphere. This is the equation of the sphere. This is the equation of the sphere in terms of rho and phi, of rho, theta, and phi. Is there a theta? No. Does there need to be? No. I'm good. I don't need to have a theta. But it's rho equals cosine phi. Okay, so then how would I find the top surface of my ice cream cone? Well, that's just gonna be cosine of phi. Rho is gonna be a function of phi. Oh, okay. So going back to my limits of integration, I'm gonna go from 0 to cosine of phi, rho squared, sine phi, d rho, d theta, d phi. When theta went from 0 to 2 pi, and phi went from 0 to pi over 4. Boom, now we can integrate. Okay, now, sorry, this is phi, not theta. Okay, so now let's integrate. Let's integrate with respect to phi, with respect to rho first. So it's going to be rho cubed over 3 sine phi, and we're going to go from 0 to cosine of phi. Okay, so if I plug in this, I get cosine cubed phi 1/3 sine phi. Okay, and then if I plug in 0, can everybody see that's just going to go to 0? Right? Plug in 0. We're good. Okay. So this is this. Okay, so now we're going to integrate 0 to 2 pi and 0 to pi over 4. Right? Okay. Okay, and then this is d phi, or d theta d phi, d theta d phi. Okay, so now we're going to integrate this with respect to theta. Well, there is no theta, so the whole thing is just a constant. And so I'm just going to integrate, and I'm going to go, and I'm just going to, does everybody see that by integrating this on theta, I'm just going to multiply by 2 pi? Can I just go directly to the 2 pi multiply? Is that okay? I mean, do you
I
really,
don't quite see it, but
what, say that again?
oh, I don't quite see it.
Oh, you don't quite see it. Okay. Okay. So if I take, this is going to be 1/3 cosine cubed phi sine phi theta, right? Does that make sense? Because the whole thing is just a constant. If I'm integrating with respect to theta, it would just be a constant. And so it'd be like, take the integral of 3. What's the integral of 3 dx? Isn't that 3x?
Oh, yeah, that makes sense.
Okay. And then put in 0 and 2 pi. Well, what are we doing? We're just going to put in 2 pi here. That's going to be 2 pi times this whole thing. Plug in 0. We're just going to get 0. So what's the net effect? The net effect of this is that all we did was really multiply by 2 pi. Okay, so this is 2 pi over 3 cosine cubed phi sine phi d phi. Okay, and this is 0 to pi over 4. Now we have to just integrate this with respect to phi. Oh, okay. Well, this is just the easy u sub. This is just easy u sub. Okay, u is equal to cosine phi. Okay, du is equal to negative sine phi d phi. Okay, look, there's my integration factor. Okay, I just have a negative du this time. Okay, so this is going to become, okay, if I want to change my limits, what's the cosine of 0? Cosine of 0 is 1, right? What's the cosine of pi over 4? Radical 2 over 2. Okay, nice. Okay, so this is 2 pi over 3. Okay, and then, oh, did I integrate yet? No, that's right. That's right. Okay. Yeah, well, I didn't integrate yet. So this is negative u cubed, right? Du. I think that's right. I'm going to go with it. Okay. Okay. So now what is this going to become? Well, this is going to become negative u to the 4th over 4 from 1 to radical 2 over 2. Okay, that's kind of cool. Okay, and so this is, I can pull the 4 out if I really wanted to. 2 pi over 3. This is, I could cancel this 2 with this 4. That would be a 2. So this is really pi on 6 of negative u to the 4th power from 1 to radical 2 over 2. Okay, and then what's radical 2 over 2 raised to the 4th power? It's just 2/4, which is 1/2. Is that right? No, that doesn't make sense. It's radical 2 to the 4th power and 2 to the 4th power. That's 16. 16 is going to be on the bottom. I'll just write it out. I don't want to just do it in my head. 4 minus a minus 1 to the 4th power. Okay, so pi on 6. Okay, and so then this is going to be 4 on top, I believe, and 16 on bottom. Is that right? So this is negative 4 over 16, which is 1/4. Yeah. Okay, and then this is going to be plus 1. Okay. So this is 1 minus 1/4, which is 3/4. And this is pi over 6. Oh, look at that. That cross cancels. And I'm left with pi over 8. That is beautiful. That is some beautiful mathematics right there. Okay, I am not going to cover 15.8 or 15.9. I'm just going to cut it. Okay, it's just, I don't have time to cover it in depth. And so I'm just going to cut it. So we're not going to do 15.9. I don't even know if there's homework for that. Did I assign homework for 15.9? If I did, I'm gonna get rid of it. Okay, so it's just too difficult, and I don't have time to cover it in this course right now. So I'm gonna blame COVID. But anyway, so that's it. That's all the material. We're only gonna do up to 15.8 for the exam. I'm not going to cover 15.9. And yeah. Okay. Okay. I'll see you guys later.
Thank you, Professor.
Thank you.
Yeah, you're welcome.
Thank you.
I have a quick question about the last problem. Instead of doing the U sub, I was wondering if you could integrate by just doing negative, like if you take the 2 pi out and then you do negative 1 over 12 times cosine to the 4th, and then the pi, and then you do that from 0 to pi. Would that work?
Say, how far back are we going here?
Oh, just like right before there was the U substitution.
So right before the U sub, okay.
Yeah, like if you like with the 2 pi over 3 cosine to the 3rd and then sine, if you could just like would it be possible to do the same thing but without U and just do like negative and then some constant cosine to the 4th and then sine, or no sine?
No, because you have to, yeah, because you what you have there is you have two functions of phi, right? I mean, if you want to integrate by parts, go right ahead. But to me, that's a lot harder than just doing a U sub.
Oh, okay. I guess I might have done it wrong, but I thought if I had like something along the lines of some constant and then cosine to the 4th, like negative some constant times cosine to the 4th, then by the chain rule, it would get the same thing. Or I mean, I might have just
Well, that's
messed
what
up,
we're
but I'm
doing.
not sure.
We're actually we're doing the reverse of the chain rule by doing a U sub,
Oh, okay.
right? We're undoing the chain rule.
Right. Okay. Yeah, that makes sense. Thank you.
Sure.
Bye.
Bye. Thank you for your participation. I appreciate it. Did he say something about his grandma? Bold of you to assume, oh, that's what she said. Bold of you to assume that I'm smarter than my grandmother. I don't know. Just bold. Bold. I haven't heard that.